Swayam Prabha. Digital India. Educated India.
Welcome back, and in lecture 58 we will talk about urban flood management and drainage plans, and this is part 1. So, the different concepts that we will cover are on stormwater drainage, flood modeling, and flood modeling using basic approach and using GIS, and then we will look into a case study. So, when we talk about stormwater drainage, the main issues that we face in our urban area is the rise of impervious areas and also filling up of low lying areas or sinks. So, that means this has not only increased the volume of runoff that is generated in an urban area, but also the time it takes for runoff to travel from the point where the rainfall falls on that catchment and then to the point where it is being collected or that particular drainage channel, that time is also reduced. And that is resulting in increase in the incidence of flooding and even during normal rainfall events. That means with very little amount of rainfall also we are seeing that water is certain areas are getting inundated or there is some amounts of flooding. So, as you can see in this particular image, the red line is the larger base flow. So, that means the pre-development flow, that means before this area was developed, and you can see the base flow was pretty extended and it was larger. But now after development, you can see the runoff volume that is being generated is generated, the volume is also high and it is generated much faster. So, there is reduced peak time, and then the base flow is actually reducing, and we can actually see that there is after this time there is not a problem. That means the base flow is low. So, the drainage channel which used to cater to this kind of flow of runoff, now this excess volume of water is not able to be taken care of in those drainage channel, and that is actually creating the flood. And also the time of this rainfall to this runoff, maximum peak runoff generation is also getting reduced. So, in addition to this presence of impervious areas and all, there are other issues as well. For example, when in some areas, new areas particularly, wider diameter pipelines are being laid, and then they are connected to lesser diameter older pipelines in the main trunk lines, or in the main city area they are connecting these pipelines to older pipelines which are actually of smaller diameter. So, that also will lead to flooding, because when a larger diameter pipes connect to a smaller diameter pipe, the water cannot pass through the entire water, because we are already having a larger pipe, and this water will not be able to go into this drainage line, and this will remain or come out from the manholes or from the manholes, and that will create flooding in those particular nodes or those particular areas. So, this is one. Then aging infrastructure and actual status of infrastructure is also not known. In most urban areas you will find many of those drainage stormwater channels are blocked, and we do not have any information on those things. And then also some areas there may be collapse of those particular drains and all. So, that is actually preventing water to pass in the same rate as it is supposed to pass. So, that also is reducing the quantum of flow, and that also is leading to flooding. And then in Indian urban areas, there are other problems that we face, that is historical rainfall records are sometimes not available, lack of data on the sewer and the storm drainage infrastructure, and so this data unavailability also becomes a big challenge in whenever we plan for stormwater drainage in Indian urban areas. So, when we talk about floods in urban areas, there are different kinds of flood. The first type is fluvial flooding. There are other kinds in addition to the 4 types that we have given here, but these are the main 4 types. So, fluvial flooding is when a river overflows its banks, then we call it fluvial flooding. Now, then comes pluvial flooding, which basically means that after a rainfall event, the water that is generated or the runoff that is generated because of that, that is creating a flood, and that is not related to the water body or the river that is adjacent to that particular urban area, but it is primarily because of the rainfall that falls on the urban area, and that is creating flood in that particular urban area. So, that is pluvial flooding. And then coastal flooding is there, that is when occurs during storm surges, that is high wind pushes seawater to the coast, or it is because of some tidal surge. So, that is when coastal flooding happens. And then there is groundwater flooding, that is when there is excess amount of groundwater, it may also create flooding in some areas. Maybe you are recharging a particular area, then the aquifer is filled, and then there could be groundwater flooding, or there could be some other cases where also groundwater flooding can happen. So, during pluvial flooding, that is urban flooding from intense rainfall or a flash flood, overland flow and channel flow can converge to nearby streams, resulting in fluvial flooding as well. So, pluvial flooding and fluvial flooding can also happen together. That means, when too much amount of rainfall is generated into in an urban area, and it all flows into the nearby channel, and then also it could create some amount of fluvial flooding from that as well. So, how do we do or determine the spread of flood or the occurrence of flood? So, we need to conduct flood modeling for that, and for this the different design and decision support tools are the hydrologic and the hydraulic models that already we have learned earlier. So, we use those models to actually determine the extent of floods and so on, but there is a certain strategy to it how we use those particular models. So, usually a properly planned and designed storm water drainage network is required to prevent urban floods. So, whenever we do flood modeling, we actually test if the existing infrastructure is adequate to cater to this kind of runoff or this kind of flooding, or what has to be done to prevent that kind of flooding and so on. So, usually urban stormwater drainage are made of 2 systems, one is the minor system, another is the major system. So, minor system you can understand, this is the network of subsurface stormwater drainage channels. So, if there are sewers which can convey the stormwater, then these are subsurface stormwater drainage channels, which forms the minor network. And so, we already have learnt how to determine the flow in these particular channels, and we know that the return period is taken for 2, 5 or 10 years, depending on where or for what purpose we are designing this particular channel. And similarly, major systems are refers to surface networks in the urban area, which is into streets, natural and artificial channels, and this is also referred to as overland flow. That means the water flows over land, and sometimes it may flow along the streets, sometimes flows along the natural or the artificial channels and so on. So, in this case, the return period is a little bit more, that is 25, 50 or 100 years, that is the return period that we consider. So, we have minor systems, that means water is collected, enters into this minor system via the inlets, and then it flows, and we estimate the time of concentration and then again the rainfall that is as per that particular time of concentration. We will consider that and determine what kind of water comes to different nodes and what is the maximum volume of water that comes to different nodes, and then based on that we design the channels, right. So, sometimes when there is more rainfall than expected, then what happens, the water that is coming to that particular node is actually more than the design profile of that particular section, and that is when the flooding happens. So, this excess water we can assume that will come out through the manholes or at this particular sections or at this particular nodes, and that will create flood in that particular area. So, similarly, the water that and that means the water is first getting into the sewer system. Even when we are estimating that the maximum amount of water based on the time of concentration and all for that particular catchment comes to the sewer network, but because it is not able to cater to that, that excess water is coming out via the nodes. Maybe physically it is not exactly like that, but when we solve this when we do flood modeling, we actually think in that way. So, what the excess water that is coming out of this node now actually spreads over the surface. Spreads over the surface means they will spread on that particular land area where this and then it will move along this particular this streets or this particular natural or artificial channels, and this forms the overland flow. So, water exchange then because now water is flowing along the water this particular over the land, then it will also come in contact with some other inlets or along the sewer network or where the stormwater sewer network, and then water will also enter into those particular inlets. So, there is exchange that can happen between both the major and the minor system through inlets and manholes. So, that means flooded that means at certain nodes excess water we can estimate the amount of water which would be excess, and that actually becomes overland flow, and from overland flow also water can get inside the inlets as well. So, flood models attempt to link these two systems and simulate stormwater overflow and street flooding. The complexity of this linkage actually determines what sort of model we determine. We can have very easy models, but at the same time we can have very complicated models as well. So, flood models attempt to link both the major system and the minor system and simulate stormwater overflow and street flooding. So, that you can see roughly on this particular image that this entire street has got flooded, because the street is also sometimes designed as a drainage network. That means the surrounding water will come to the streets and then get into the sewer network via those particular inlets, but because the sewer is totally filled, it is not able to take in, this water remains on the street, and that is what is creating the flood. And then again the water spreads from the street to the surrounding areas. So, flooding at nodes spread in the surrounding area and can also reach other inlet points, right. So, that is, you can see this is a practical example. You can see this manhole is raised up and water is coming out of the manhole. So, that means even though there may be no rainfall in this area, maybe rainfall is happening in some other area. So, the water is traveling along this particular manhole, right, and the water that is reaching that manhole or estimated to reach this manhole based on the time of concentration and the catchment area is probably exceeds the diameter of the manhole, and that means this profile or section of the manhole is not able to take care of that, and water starts coming out of this manhole. But in most cases what happens is we have the this particular manhole, that means there is a sewer line below. So, there are inlets to the sewer line. So, because there is the sewer is filled, no water can enter into the through the via the inlets, because everything is filled, and that creates flood in that particular area. So, the basic approach, the most easiest approach is to consider that we assume that for the minor network, that is the sewer network or the subsurface stormwater drainage, we use 1D hydraulic modeling for determining the subsurface stormwater drainage, and for this we can use the SWMM software that we have learnt earlier. And so this 1D hydraulic model, if you remember that from the Saint Venant's equations that we have done, there was kinematic wave, diffusion wave, and then we are using those for determining that how the water is actually traveling through a particular stormwater channel. So, that is and 1D is basically one dimensional, in one direction the water is flowing, that is along that particular stormwater channel. So, that is where when we design a minor network we can go for 1D hydraulic modeling, and what happens is using SWMM we can determine which are the nodes that are getting flooded. That means where that volume of water that comes to the node and the capacity of that node is not adequate, we can determine that, and we can also determine the total volume of water that is flooded, that is creating the flood, and then we can use GIS to model the inundation or the flooding because of that particular water. So, that excess water at the node which is created which is estimated and that is creating the flood, that could be taken in GIS, and then we can model the inundation or the spread of flooding because of that excess water. So, this could be termed as the overland flow. So, flood depth and spatial distribution which helps in and once we know the flood depth and the spatial distribution of that flood depth or that flood event, we can determine the hazard created by the flood. So, hazard prediction comes after we can determine flood depth and the spatial distribution or spread of this particular water. So, this approach is cost efficient and relatively easy, and that is mostly followed in urban areas and in most, but we can also have other approaches as well. So, this is called the dual drainage approach, where interaction between surface and underground flow components are considered. So, that is why it is called a dual drainage. So, we not only consider the drainage in the minor system, but also in the major system or in the overland system. So, within dual drainage approach, we can again have two approaches. One is called 1D approach and the other is called 1D approach. So, what happens in 1D approach? So, surface flows, that means we already have stormwater which is flows which is modeled using 1D. Then similarly, surface flows are modeled as open channels or ponds and solved using 1D Saint-Venant's equation. So, over here the surface flows, we considered that whatever flooding happens at a particular node, that actually spreads along the street, that means or along that particular drainage channel. So, that means here also we assume 1D flow or we use 1D Saint-Venant's equation to solve this. So, street is considered as an open channel similar to the flow in the underground subsurface drainage network. And usually urban overland flows is not that simple, because it does not only passes along the street, it will spread in multiple direction and it usually shows distinct two-dimensional behavior. So, that is where we go for 1D approach, where we use 1D for determining the subsurface stormwater flow, whereas we use the 2D approach for determining, we use 2D shallow water equations for surface flow and 1D for the drainage network. So, 2D shallow water equations are utilized instead of the 1D shallow water equations, and then that is used to determine the overland flow at a particular area. So, 1D or 2D dual drainage models along with detailed DM data are used to model floods. So, how we are able to do this 1D 2D approach? So, usually we use stormwater management model for the 1D determine the flow in the 1D sewer network, and the SEM SWM output is used. That means that the node flooding data that we generate out of this SWM, that is utilized, and this is used with the 2D overland flow models to simulate and visualize flood area. So, we give this input as which are the nodes that are flooded, how much amount of volume of water is getting out, which is excess in those particular node, and that is taken as an input for this 2D overland flow models, and they show that how the water will spread over the surface from that particular area. So, node flood discharge like at a manhole can be estimated by SWMM and transferred to the overland flow model, and which are those overland flow models like XP SWMM, PC SWMM, MyCarbon, IBER, which is also free, and Flow 2D Pro, and these are the 2D overland flow models which can be combined with SWMM. So, this is a model system. Similarly, we have another model system. So, over here you can see these are all commercial softwares, MyCarbon, PC, SWMM, these are all commercial softwares. IBER is a free software, but it is not that commonly used. So, the alternative to all this is, instead of even using SWMM, we can use two other softwares, which is the Hydrologic Engineering Center Hydrologic Modeling System. This is made by US Army, and Hydrologic Modeling System, that is HEC-HMS, and Hydrologic Engineering Center River Analysis System, that is HERAS, which can be used to determine channel flows and overland flows, that is catchment inundation for known precipitation events. So, here both channel flow, that is 1D, as well as overland flow using 2D could be utilized, could be designed using this two softwares, which are also freely available. So, that is why I am showing you that these are the two free softwares which are available, using which we can model floods. But if I want to do 1D approach, then SWMM is good enough. So, flow exchange, as we were discussing, it could be a unidirectional exchange from sewer network to the surface, That means at node the flood happens, and we assume that from that point the water will spread in all directions. Or it could be a bidirectional exchange, that is flows from the overland flow that is generated also enters into the sewer at other points, right. So, it could be a bidirectional exchange which allows flows to enter into the sewer. Now, how we can model that? To model this, we need to do a time stepwise simulation where both the processes, overland flow and sewer flow, can be conducted. That means, first we compute the values for the sewer flow. Based on that, flooding is generated at certain nodes, and then from there we calculate the overland flow. Some amount of water gets back into the sewer, and that again contributes to the flow in the sewer. So, we can do it at multiple time intervals to see what are the effects. So, that is how some people have also modeled flooding in particular urban areas. So, in the basic approach, so in this particular lecture we will we will learn about the basic approach where we use SWMM, or we can use some other softwares as well. So, SWMM, as you know, is a dynamic hydrology hydraulic runoff quantity quality simulation model, and primarily for urban areas, and this could be used for planning, analysis and design of stormwater runoff, combined and sanitary sewers and other drainage systems. So, we have already learned this. And similarly, we have also learned that how to determine catchment areas for an urban area, and we have shown you that hydrological analysis based on DM could be conducted to determine the natural stream orders in a particular area. We have also learned the node based method, that is geometric method, where we have considered important nodes or flooding points, and from that we can create Voronoi diagrams to determine this, or using this Thiessen polygon method we can determine the area which is contributing to that particular node. So, both the methods are there, and in areas of flat terrain geometric methods are suitable, but to predict overland flow terrain is important. So, we know that, to determine the catchment in flat terrain this node based method is fine, but as soon as we want to understand the spread of water from a particular node which where this excess water is generated, there we need to understand the terrain, otherwise how we will know that in which direction the water will spread. So, that is where terrain becomes important. So, catchments are delineated using combined approach of both this hydrologic and geometric method, and most sewer networks are aligned with streets, and so we can modify the catchments as per that as well. So, we have learned this basic process of determining a catchment for a sewer network. So, we will follow more or less the exact same process. So, node floods are initially estimated using SWMM. We have also learned how to determine node floods when we have shown that when we have determined SWMM, and then node floods are converted into catchment or grid floods using an inundation algorithm. So, suppose we have a sewer network, we have different nodes, we determine what is the flooding in this particular node, then we determine the inundation, that is the spread of flooding, using some algorithm, that how this could be determined, and that means node floods are converted into catchment or grid floods. So, that means this node flood point, this we now transfer that how much this will spread in a particular area. So, let us see the example when we use a basic approach using SWMM software. So, you remember the interface of SWMM. So, these are the catchments that we have determined, and we can also see these are the nodes and these are the sewer lines. So, that means water actually travels and reaches this particular inlet points, and from there the water travels. Now, SWMM can be used to generate profile plots showing how water surface depth varies across a path of connected nodes and links. So, this is the sewer network. So, we determine that start node is maybe 1 and the end node is 18, and so these are the different links in the profile. So, we need to find the path in which water will flow from node 9 to node 18. So, once we determine the path, this is what is shown. So, this is the path, this is the start node 9, then it goes to start node 10, then it goes to node number 10, then to node number 21, 22, 16, 24 and so on. And in each node there is a manual, because there is change in direction or alignment and so on. So, we can see the volume of water in each of these sections, and this could be determined in SWMM. So, based on the rainfall event that has happened, we can run the simulation once we have put in all the data, and we can determine the volume of water in each of the sewer sections. and then based on, we will see that wherever there is flooding, the water is reaching the top of this particular manhole, and we will see the water, there is a mention of so much amount of excess water. So, water elevation at a particular time could be determined, right. And we can see that in SWMM, flooding occurs when water surface at a node exceeds the maximum assigned depth of that particular node. So, we can see, we have already seen the node depths over here at every junction, what is the average node depth, and you can see that the maximum depth over here is 0.3 to 0.3 feet, and if it exceeds the ground level, then probably there would be flooding. So, node flooding, we have seen that at node 10 over here, number of hours of flooded hours is 2.82 hours, maximum rate of this is 4.53 cubic feet per second, and it also gives us the time when the flooding happened, when the maximum flooding happened, that is at around 4 p.m. and total flood volume is also given over here. So, maximum ponded volume in 1000 feet is also that you can determine from over here itself. So, once you know that at a particular node there is flood, then usually in SWMM, in further calculations, we don't decide, we don't look into this. That means the water is lost from the system. That means we don't consider this further. But this water could be considered as ponded, that means gathered on top of the node or detention basin and reintroduced into the drainage system later. So, that means this water will be ponded over that particular node because there is excess water, and this could be reintroduced into a drainage system later on. So, flood volume estimate can be used for further analysis, and models can be enhanced by introducing roads and other paved areas as open channels as well. So, we can also design, instead of not only subsurface drains, we can also design the roads as well as open channels to understand that some volume of water would flow through them, but eventually we can say that that the water that flows along the particular road, when there is more water than that, then there would be excess, and then it will also create some amount of flood. So, the flood, so as we were discussing in the basic approach, we assume the node flooding at using SWMM, and the flood volume spreads from the node in the catchment area, and this can be estimated using inundation analysis, or I said that inundation algorithm is required. So, there are different forms of inundation algorithm. So, there could be non-source inundation algorithm, that means inundation is based on surface elevation, and inundation till the elevations of all unflooded area is greater than the flood elevation, or flood elevation is elevation plus flood depth in each grid. So, what it means is, I have got a line, there is a node. Now, there is some flooding in this particular node that SWM has shown me. It has also given me the time of the day when it happened, and it also gave me the total volume of flood water over here. What is the volume of water? That is excess. So, now we have to do a non-source inundation algorithm. Now, what does that mean? That means we have contour profiles for this area. Suppose the area is like this. So, maybe there is flooding over here. So, we know the contour profile, we know the volume of water. So, based on the contour profile, we will determine how much the water will spread in that area. And we usually in non-source inundation algorithm, we assume that the spread would be uniform as per the contour. We do not consider the hindrances, maybe the buildings and so on, right. So, it is based only on surface elevation, and inundation will happen till the elevations of all unflooded area is greater than the flood elevation. So, that means unflooded area, if it is lower than the flood elevation, then we will keep on we will increase the spread of the inundation. So, that is just like we know that this is the volume of water, we need to understand in this particular depressed area how much the water would be spread, or what would be the height of that water in a particular reservoir. So, we assume this entire area as sort of a reservoir. So, that is a non-source inundation algorithm, and then source inundation algorithm actually considers the regional convexity and the terrain hindrance, which is a more realistic approach. So, as you can understand, the terrain could be of different shape, and we really need to understand the suppose water starts flowing from this area, based on the slope of this particular land, the water may flow in this direction or it may flow in in two direction as well, right. So, we have learnt earlier when we have used the DM models that water flows in using the D8 algorithm that we have learned, that water flows in the direction which has got the highest slope. But sometimes water can flow proportionately to different direction based on the different slopes as well. So, if I consider only one direction flow, that is 1D, if we consider multiple directions and in different ways the water spread, then it is 2D. So, in this case, we can go for a source inundation algorithm where we can consider either 1D flow or a 2D flow. So, flow direction could be single flow direction or a multiple flow direction, but overall it is a source inundation that is we are considering. And there are other issues as well. That means, first issue we talked about, that there are terrain hindrances and then there are buildings which are also comes in the way. Flood water doesn't usually get inside the building, because sometimes the buildings are raised or sometimes they have some other protective measures. So, those has to be considered when we consider the spread of the flooding. And we can consider the spread as uniformly over the entire terrain, that is non-source inundation algorithm. We can consider the actual distance of movement of spread of the water on that particular surface, or the way of the overland flow happens, and that becomes the source inundation algorithm. So, when flood is diffused in one catchment, we usually sometimes consider that the catchment as the boundary, and whatever flood volume that we have estimated, we consider to be spread on the entire catchment, and we determine the height of the flood. But that is not practically possible, because the catchment is a abstract. We have designed or determined a catchment based on our requirements, right. But flood water doesn't understand what is a catchment, right. It will spread till it can spread. So, that means that consideration of boundaries becomes important. Then total flood volume of all nodes in a catchment sometimes are added up and then spread in the catchment area. So, this is one approach, but again it is a crude approach. Inundation is not limited by catchment boundaries. So, that I was just explaining, and similarly building footprints needs to be considered while determining inundation. So, these are the different considerations that you can also make while you determine this flood volume, how it will spread in that area. So, let us look at a case study. So, this paper was written by, this research was conducted by Huang and Jin, and this is a methodology for simple 2D inundation analysis in urban area using SWMM and GIS. So, this is the basic approach that people use. So, first of all, you have to create a GIS database preparation, and this was also done for this research. Then the SWMM model was actually utilized, then catchments, conduits, junctions, outfall characteristics, catchment divisions, and their configuration was all has to be input into the SWM model. And the infiltration model in SWM, as you know, could be, you can use CN method, you can use Horton. So, multiple methods could be utilized. So, once you have the land use data, precipitation data, pipe network data, then DEM data. So, once this kind of data is there, then we can process the data, and then we can determine in the SWM model, we can actually use this particular data and put in this data, and then we can run the SWM model. So, we can run the model for for multiple scenarios or for multiple cases, and then we can determine the node flood volume. And once the node for flood volume is determined, then we go for inundation analysis, and we determine the inundation area, the total inundation depth of that particular area, and we can make GIS map for visually representing that. So, let us see how it was done. So, first the catchment properties were input into the SWMM model, the area of the catchment, width of the catchment, slope, land use of the catchment, all these things were entered. Then impervious, non-impervious, impervious, then depression storage impervious rates, and then this depression storage pervious rates, then maximum rate or minimum rate and decay, these all were inputted into the SWMM model. And this Manning's coefficient as per land use of catchment divided into impervious, permeable and depression areas, this was input. That is what it was considered there, shown here. And then similarly max and steady infiltration rate of catchment, so that was entered. So, that is that maximum rate, and then decay refers to the infiltration attenuation coefficient of the catchment, so that was also entered. So, here you can see this is the land use type, impermeable, farmlands, constructions, woodlands, rivers and so on. Then Manning's coefficient for each of these particular catchments were actually determined, and once that is determined, then based on the natural slope of that particular area or the DM of that area, the natural flow channels were determined, and this you can see the natural nodes and the natural flow paths. And if you remember from earlier lectures where we have determined the catchment and then we have used ArcGIS actually to determine this, from the DMs we can determine the natural flow paths in a particular area, right. So, this actually shows in which direction the water will flow and along which channels the water will flow. But this is good for larger catchments or for larger areas, but again in urban areas, particularly in flat terrain areas, we have to depend on the node based catchment geometric methods of catchment determination, and this is what has been done. So, this is the network, the sewerage network or the stormwater network in that urban area, and for each of these particular points, this we determine this this Thyssen polygons, which actually determines the catchment that is drained by this particular inlet point. Now, if you see this particular image, this particular inlet was not there over here, but this is taken from this one. So, actually both has been combined, the actual drainage network and the natural flow network, both have been combined to create this final nodes and conduits, final nodes and catchment areas for this particular catchment. So, it is a hybrid approach where we combine both the approaches together, and this gives a more realistic the stormwater network or catchment for a particular area. So, in the D8 algorithm could be utilized from DM, and then the stream network could be determined. Then flow paths and the node start, end and intersection points are analyzed, and actual drainage network is checked over here. If some nodes from the stream network has to be retained, so both of these are combined. Pipe network can be extended to these particular nodes, and open channel can be also used to represent this particular flow. So, that means we can assume that there are some drains or some natural drains could be also put in. So, both it could be, we can say that the pipe network could be extended to this particular point, or the sewer network could be extended along this particular channels, or we can say that there could be open drains for this particular channels. But overall this together makes up the stormwater drainage network. And so, initially it was 167 nodes and 137 conduits in this particular case, but after the combined approach, so this is final, total 198 nodes and 21 outlets were considered. So, next based on this node based on this network data as well as the catchment data, the node flooding summary in SWMM was calculated. The SWMM was used to estimate where the flooding happened, and which also shows the total flood volume during the simulation. So, after that the inundation analysis was conducted, and inundation extent and depth using this digital elevation model and a diffusion algorithm was considered. So, of course, this depth and extent will be influenced by the DM of that particular area, but a new diffusion algorithm was utilized in this particular work. So, how does it look like? So, source inundation, that means at each node there was excess water, this needs to be spread. So, multiple flow directions was considered. So, from diffusion sources of the nodes, and diffusion happened on a basis of terrain using trial method and considering water balance principle, and diffusion area is gradually expanded if the current flood elevation is greater than elevations of the neighboring grid. So, instead of taking the entire digital elevation model and determine how could be the spread following in the basic approach that we were discussing, this is a little bit modified approach, where first this is the node from where diffusion is happening is determined, then gradually it is expanded. That means, we expanded by one cell in each direction, and we see that is this if the level of this area is higher than the flood level, and if it is so, then we expand our area for where the flood is occurring. then we keep on expanding in different direction, and that is what has been followed, and that is the that new inundation algorithm that has been proposed in this particular paper. So, this method is called seed spread method, and it is used to overcome the spatial discontinuity issue. So, that means otherwise what happens, we can actually say that for each zone how it is spreading to the surrounding zone, we can determine following this seed spread method. If we were considering that overall area and how much is the depth and understanding the total volume of flood, and we just divide that flood volume for this total surface area, of course based on the contour profile, and say this is the extent of flooding, there we are not considering the discontinuities in certain direction. That means because of presence of certain ray structures and all these things, we are not considering that discontinuity. But here we can do that because we are gradually spreading from this point to the different directions, right. So, flood volume of node is equal to V, flood elevation is equal to H, and area is the area of each grid. So, H is equal to V by A. So, in case grids are inundated from two nodes, that can happen, then nodes volumes are merged and the new node is formed. So, that means there is one node, suppose there is another node. So, flood comes to both these points, the volume of flood is extending to both these points. So, in this case we will add these two node volumes and we can increase the catchment size as well. And the flow and then we can merge that and a new node can be formed, and then from there we can do the spreading after that. So, the flow direction depends on the grid elevations and can flow into any grid, and there is no boundary in the algorithm, also no boundary was considered. So, this is a improvement on the simple GIS method, but at the same time it is still not overland flow or following 2D approach. This modeling is not done, it is still a simple GIS approach. So, finally, we can see that for this particular area, this is expanded over here, you can see that this is the spread of flood, and here the flood heights have also been categorized, and flood elevation is given in meters, which in some areas it is 11 meters, whereas some areas it is as low as 0.01 meters. So, that is how this entire area's flood model has been determined. So, to conclude, flood models link storm sewer overflow and street flooding. Streets can also be considered as open channels to determine flow and flooding. Urban flooding can be determined using a basic approach where 1D hydraulic modeling is used for determining subsurface stormwater flow and GIS for modeling inundation, that is overland flow. And urban flooding can be determined also using dual drainage approaches considering both subsurface stormwater drainage and overland flow. So, these are the references that you can use. Thank you.